Okay, everyone, let's get started. Last week of class. It's hard to believe. Semester flew by. I understand Charles did a good job filling in for me last Wednesday. I'm going to briefly review the material he presented, and then I'm going to try to get as much done I'm going to combine chapters 6 and 7, cover selected elements of 6 and 7 after that. Okay.
In terms of prep for the final, which is I believe on Wednesday?
Friday, yeah. Keep the current color scheme. So what was your question? Oh, you mean when we'll review? Well, I'll take some time on Wednesday.
Okay.
And
I imagine the stuff will be out, the practice stuff, because that was very useful for the recent test.
Yes, yeah. I'll post I'll post a list of practice questions from the text, and we'll have one more quiz this week, our last quiz. And yeah, like I said, we'll have a brief review on Wednesday. Okay, so to finish up Chapter 5. Chapter 5 was a mishmash of a whole wide range of topics. It started out with adders and then went into subtractors and comparators, and then fixed point and floating point. Everyone okay with those topics? Any questions? Okay, and then I think the first thing that Charles covered on Wednesday was counters, right? Yep. That's where you started? So counters are a common pattern that you see in digital circuits. You can build one really easily. You just take a multi-bit flip-flop or register, and then you use that to hold the current count. And then you take the output of that and you feed it back into an adder, and then the other input on the adder is a hard-coded 1. So every cycle it will add 1. It'll accumulate to its count. Another common thing you see are shift registers, which is where you have a set of 1-bit flip-flops, and they are connected serially. So the Q output of each flip-flop feeds into the D input of the next one in the line. The leftmost one has a 1-bit input, and so every cycle you can feed a new value into the first flip-flop, and then all the other values get shifted down by 1. The purpose of this, as the book notes, is that you can make a serial to parallel converter of this. So if you can imagine, if you have 16 of these connected in 16 cycles, you feed it. You can load these up by feeding 1 bit at a time serially, and then all of those 16 bits will be presented here that could be read out in parallel. You guys with me? You can also create a variant of this with a parallel load where you add a mux to the input of each flip-flop, and that mux selects between getting the next input of each flip-flop from the previous flip-flop to the neighboring flip-flop, or you can have another option. Option 1 is being able to initialize all of the bits in the shift register in parallel in one cycle through the other input on the muxes. So looking at this sort of at the top level, you have an input called load, an input called SIN, which stands for serial in, but then you also have a multi-bit input, D, which is however many bits this register happens to be. This is designed to be scalable. You can make this as big as you want by adjusting N. And then if load is 1, that means that on whatever clock edge load is 1, you'll be loading in the D input in parallel. And if load is 0, then you'll be loading in bits serially from S in. So this can create a serial to parallel converter as before, but this time you can also do a parallel to serial converter. You can load in bits in parallel and then shift them out. So I could, in one cycle, I can load 16 bits into this thing, and then I can take the next 16 cycles, shifting out each of the bits once per cycle. Make sense? Now, what is this useful for? A lot of interconnects these days are serial, are high-speed serial. PCI Express, SATA, Thunderbolt, HDMI, high-speed networks, they're all serial. And generally speaking, if you had, like, say, a chipset, a chip that was communicating with a high-speed serial, you could load in the word that you want to send out in parallel, and then you shift out the bits really fast over the serial link. You guys with me? So this is sometimes called a SerDes, serializer or deserializer. And of course, that would be at the transmitter, and at the receiving end, you would do the opposite. You'd bring in bits serially, and then you read them out in parallel. Okay, so switching to another topic, memory arrays. An array is just that. It's a two-dimensional array of bits. It's arranged kind of like a matrix in rows and columns. So there's one bit at each. There's one bit for every row times columns, right? In there. There's different types of memory. So when I'm talking about memory arrays here, I'm being very general about it, because you might be thinking, well, memory, you're talking about like RAM, like computer main memory, like you upgrade the memory in your computer and you put in the DIMMs, right? But there's all types. Memory is, I'm being kind of general. There's DRAM, which is like main system memory, SRAM, which is generally is the on-chip memory on a processor. So like it would be like your cache or any kind of what they call scratch pad memory on your on-chip memory, which is usually faster but smaller. And then ROM, which could be like flash memory, solid state disks, that kind of stuff. But they're all sort of similar in the sense they're all organized in a similar way. They're organized as this grid of bits. Now, whenever you refer to any type of memory, you generally refer to it as the depth, and then by x, and then the width. So you'll see this a lot, like if you look at part numbers on actual memory chips or memory modules. So there's the depth, which is the depth refers to the number of addressable entries in the memory, the number of rows. So that's the depth. Think of it like depth is rows and width is the columns. So the depth is going to be the amount of data you get out of the memory when you access it. The width is the amount of memory you get out when you access it, and the depth is the number of individual elements that you can access. Sorry, I screwed that up. Make sense? So if I had a 1024 by 32 memory, for instance, I would have a 1024 words of 32 bits each. That would be a 1024 by 32, right? Okay. The number of address bits would be log base 2 of the depth. So in that same example, if I had 1024 depth, then there would be log base 2 of 1024 is 10. That would be a 10-bit address. But the total size would be 1024 by 32, so 32 kilobit. If I want to convert it to kilobyte, then I would divide by 4. I'd 8 kilobyte. Okay. Let's see. All right. So internally, there's this terminology that's, I think it's applied to even flash memory. It's a common terminology. You have this bit line where the bit line is generally associated with the columns, right? And then there's the word line that selects one of the rows. This is the easiest way to think about it. So the bit line is they're shown here as this vertical line. The bit line is what comes out, like if you read the memory or write to the memory, the bit line is the data that comes out if you're reading or goes in if you're writing. And the bit line is is multiplexed. So depending on which row I activate inside the memory, I would use the same bit lines to be able to read or write different rows. The row is selected through the word line. So you could think of it like every bit in the memory is at this kind of intersection between word line and bit line. So if the word line for a bit is activated, is charged up, then that bit will be connected to the bit line. Make sense? Okay. All right. So this is an example of a 4-row and 3-column memory. The word lines are generally attached to a decoder. So you put an address into the decoder. This is a decoder sort of in the classical sense, where you put an address in that's binary encoded, and then this is converted to a unary encoding or a one-hot encoding where there's 2 to the n, where n is the number of address bits coming out, and one of those will be activated for each address. Actually, you would have one decoder for each port on the memory. I'll talk about ports in a minute, but in this case, put an address in, it activates one of the word lines. It'll activate one of the 4 word lines, or one of the 2 to the n word lines, where n is the number of address bits. And then whichever word line is activated, that word, which is essentially that row, all the columns associated with that row, will be connected to their corresponding bit lines. Okay, so there's different types of, the question now is, what are in these boxes? Like, how are these bits physically stored in a memory array? How does that work? Because this is, you can see this is very abstract. It just says stored bit. There's multiple ways to do that. And that's defined by what type of RAM or ROM you have. DRAM stands for Dynamic Random Access Memory. That's the main system memory that's used in most computers. And in DRAM, these boxes are capacitors. So you're actually storing charge. Each one of these bits is a charge that's charged into a capacitor. Then there's also SRAM, static random access memory. And in SRAM, each one of those boxes is a cross-coupled inverter. It's 2 inverters facing one another. Kind of like the real primitive form of the latch that I showed at the beginning of chapter 3. Okay. By the way, one thing I forgot to mention, this decoder, what do you think happens to the decoder when I scale it up, when I add more of these rows? Well, the decoder gets slower, right? And this is why larger memories have a longer access time. This is also the basis for the memory hierarchy. So the bigger the memory, in terms of its capacity, the slower it is to access, and that is mostly because of the decoder time, the decoder delay. Okay. All right. Okay, so going back here, so DRAM, it kind of looks like this. This is a kind of a simplistic diagram, but the word line comes in and it's attached to a single transistor, an NMOS transistor. And then that transistor is used to connect this little tiny capacitor to the bit line. So when the word line is 1 for this row, or for this bit, it will just connect this capacitor. One side of the capacitor is at ground, and the other side gets connected through this transistor to the bit line. Of course, that'll discharge the capacitor, so it'll destroy whatever charge is in there whenever you do that. So that's a reason. So every time you read a bit in a DRAM, you destroy the contents of it, and you have to put it back in. The way you do that is also through the bit line. So this bit line here acts as both an input and an output. When you're reading this bit, you treat it like an output, but when you want to refresh the bit in here, you have to treat it like an input to also connect connect this bit line into this capacitor and charge it up, put a little charge on there. So the advantage of this is very low cost. There's one transistor and one capacitor for every bit, and as a result, DRAM is very dense. So you could fit a whole bunch of bits in there. The problem is that the capacitor here, it's kind of strange. When you design digital circuits, capacitance is your enemy, because the more capacitance you have in there, the slower the circuit is. Right? The slower it is to, because capacitance, you know, there's this time constant. The resistance times the capacitance is how long it takes you to charge up a capacitor or to discharge a capacitor, right? So that represents your rise in your fall. If you're doing digital, that's your rise in your fall time, right? And so if you have a digital circuit and you've got a bunch of gates that are connected in series through a critical path, you have to pay for that rise time all the way through the digital circuit. So that gives you your propagation delay, right? So you don't want capacitance. You want one of the purposes of Moore's law is to shrink down those transistors to reduce the capacitance on the gates of the transistors, right? Also, Moore's law shrinks the wires down too. That reduces the capacitance on the wires. So we don't want capacitance. And CMOS chips are designed to not have capacitance. That is why DRAM cannot be made on CMOS chips. DRAM chips are made in a special process called a dynamic process that's designed to have as much capacitance as possible. So they're two different fabrication processes, and this is why you cannot combine logic and DRAM on one chip. Cannot be done. People have been trying for 40 years to do that, because that would be phenomenal if you could do that. That would solve the memory wall problem, potentially. Right? Think about it. You'd have one chip. Everything in the computer would be on one chip. Your processors, your memory, you could put everything on one. You can integrate everything. It would be less expensive to manufacture something like that, and it would potentially be much faster, because you could do the processing right there next to the memory, as opposed to having to go off chip and through a circuit board, right? Which is slow. But it can't be done. There's no way to do it. You can put logic in a DRAM chip, but it would be unusably slow because of the capacitance. And likewise, you cannot put DRAM onto an SRAM, onto a CMOS chip, because it wouldn't have enough capacitance to work. It would have to be refreshed so often that it would be unusable. So anyway, that's the story with DRAM. And then SRAM is the kind of memory that you do put on your processor, but in order to make that happen, you can't use a capacitor. You have to essentially use a latch circuit, which is a cross-coupled inverters. This requires, there's actually 2 bit lines that come in to change the state of this guy. And so you've got these 2 transistors here, and then how many transistors in an inverter? 2, right? And then there's 2 here. So there's 2 plus 2 plus 2. So there's 6 transistors per bit. So SRAM is about 6 times less dense than DRAM, which is why, that's why your cache on your processor is much smaller. What's the biggest cache you can get on a processor? Anyone know? So if I go buy the biggest Xeon server CPU I could possibly find, I'll get the Intel. What's the biggest one? The Platinum?
Yeah.
What's the biggest cache you can get?
I'm pretty sure it's over 20 megs nowadays.
Yeah, it's about 32 megabytes, which is pathetically small in terms of memory capacity. But that's the most you can fit. And by the way, the cache is like over half the chip. Like if you look a photograph of a processor, half of it is processor and half of it's cache. So you take half of the real estate of the chip and you just put these SRAM cells on there, and you only get 32 megabytes at most. Most consumer level chips, by the way, are much smaller, like 8 megabytes, right? Whereas a DRAM chip is how much? What's a DRAM chip?
A single one?
Yeah, single chip is 8. They're measured in gigabits.
Well, I mean, the biggest DDR4 DIMMs are, I think you can get up to 128 gigs.
Yeah, but that's the whole DIMM though. There's like 16 chips on there.
Well,
but it's
over 16.
yeah, it's gigabytes. Gigabytes. You can get multiple gigabytes. And it makes sense. So the conversion rate is about a sixth, which corresponds to this. Okay. Anyway, moving along. Multiport memory is when you allow multiple reads and writes at the same time. SRAMs sometimes have multiple ports, caches. Makes sense, right? Because caches are shared by multiple cores sometimes. So if you're sharing a memory, you need more ports, but more ports increases the cost dramatically. DRAM generally only has one port. So you can read or write, but not at the same time, and only one access at a time on even a modern day computer. If you have an on-chip memory, like a register file or a cache, then you can have, in this case, these are 2 read ports, so I have 2 addresses I can read from and the corresponding data outs, and then 1 write port. So this is 2 read ports and 1 write port. I know these are read ports because the data comes out, and I know this is a write port because the data goes in. Okay, and then system Verilog, you can make a memory pretty easily. It's pretty nice. A little confusing though at first. Basically the way it works is you declare the memory array as a local variable, logic. So you say logic RAM, and the thing about this that's confusing is you give it 2 indices, which makes sense because RAM is a 2D array, but there's 2 things about this that's weird. And when I say weird, I mean different from C and Java. The first thing is notice that the size of the dimension, one dimension is before the name of the array, and one of them is after. It's weird, right? The other difference is that this number is the depth, and this number is the width. Now the reason why that's weird is because it goes against the conventions of C and Java. In a multi-dimensional array in C, you always put the rows first and the columns second. We declare a memory, right? Also, even in digital logic design, if I give you a memory chip spec, I will always give you the rows, the depth first and the width second. I'll say this is a 64K by 16 RAM chip, meaning 64K deep, 16 bits wide. So this convention goes against both of those things, right? This contradicts everything. Nobody does width first and depth second except for Verilog. This is the only language I've ever used that does it this way. The reason they do it though is because everyone's used to putting the width of signals first, right? If this were a regular one-dimensional signal, you would always put the width first, right? And so they tack on. See, if it were me though, I would have put this number first if I was designing this language, but it's just something you have to get used to. And then now, just declaring that though doesn't tell Verilog that you have a memory. You have to also put in the behavior. So this is the read behavior, this little assign statement. And since assigns are asynchronous, this is an asynchronous read. And then when you write, it waits for the clock, and there's logic here that tells it to write if you get a write enable signal. So if write enable is true on the positive edge of the clock, then I'm going to take RAM at index A and stick in WD, where WD is the input data. That's 3 bits. That's 3 bits. So it's a 256 by 3 memory. Everyone see that? Okay. Now I can add multiple ports to this if I want. I can have more than one. A is the address, right? A, yeah, and it's 8 bits because 8 is the log base 2 of 256. If I wanted to add another port, I could add another line here and another address. I could add a A2 if I wanted to, coming in as an input, and then I could have assign RD2 equals RAM A2, right? That would add another read port if I need another read port. Okay? Okay. You covered all this, right, Charles?
Yeah.
Okay, just this is still review. Okay, and then the last thing I want to mention here is RAMs. RAMs can be used for logic as well. In particular, there's these devices called FPGAs, which are so basically, if you want to design hardware, you just have 2 choices. You can design hardware and send it out to be fabricated, which takes time and costs a lot of money. in which case, they would send you back a physical chip, an application-specific integrated circuit. Or you can use a programmable logic chip where you can design the hardware and send your, basically go through some series of steps that take your hardware design and convert it into a form called a bit stream that you can program a programmable chip with, and then from that point on, that chip will behave as though you had sent out your design for fabrication. The only drawback is the FPGA will run about 10 times slower than if you had it fabricated. Okay? The way it works, though, is it uses little tiny LUTs, lookup tables, which it's just a fancy way of saying RAM. They're just little SRAMs. And when I say little, they are, in current generation FPGAs, they're 128 entries deep by 1 bit wide. But what that allows you to create, by configuring that RAM, that allows you to create what is essentially a customized logic gate. I took the picture off. I had a picture of it, but so you just load up the RAM, however, whatever truth table you want to build, and then you take the address lines and you treat those as your inputs, right? Okay, so that's it. That's all we've got in chapter 5. Any questions? All right, I'm going to move on here to I'm going to cover the first few sections of chapter 5 and the first few sections of chapter 6. Okay, so at this point we want to start talking about how to assemble the pieces that we've got, the digital building blocks. We want to be able to assemble these into a processor. So what do we got? What is our repertoire of building blocks? Well, we've got adders, subtractors, comparators, floating point units, and RAMs. RAMs of various configurations and types. We have small RAMs and big RAMs, multi-port RAMs, right? And also there's just basic digital logic that we can use. Oh, and we can also create controllers as finite state machines, or we could create lookup tables like as logic gates or as RAMs, right? So how do we get from that to having a processor that works, that executes programs? Well, before we get into that, I want to briefly review MIPS. This book uses MIPS as the example instruction set. I was just talking to Charles there. It used to be MIPS was used for every digital logic and computer architecture course. That's changing now. Some textbooks are moving away from MIPS. They're moving into RISC-V, which is a very similar instruction set architecture as MIPS, except RISC-V is open, is free. MIPS is technically a commercial instruction set that.
Hooray for free coding peripherals.
Right. Yeah. Because if you take the knowledge you learn in this class, that if you take what I'm teaching you right now, you build a MIPS processor and you try to sell it, you'll be sued, because you're not allowed to do that. MIPS is owned by, well, I don't know who it's owned by now. It changes hands so often. It was owned by a company called MIPS, and then it got bought by Silicon Graphics, and then it got bought by Imagination Technology, and I think now Synopsys bought it or somebody. It's changed hands, but yeah, if you try to sell a processor you make with what you learn in this class, you would be sued. With RISC-V, you won't. RISC-V is very similar to MIPS, and they're designed to be. RISC-V was designed to be pretty similar. In fact, the only changes from MIPS to RISC-V are things they did, one, to avoid the copyright, and two, to fix a couple things that are kind of annoying in the MIPS, inconvenient aspects of the MIPS instruction set architecture. But anyway, the point is, and the authors of this book point out, and I agree, that if you learn MIPS, it's very easy to learn any other instruction set. Assembly language, machine language, they're all pretty similar. It's the same concept. The concept is that if you have a statement in a high level programming language, a statement like this, or a construct like an if statement, a loop, or a function call, right? Statements and constructs can be translated into snippets of assembly code. So the assembly instruction or the machine instructions are the primitive instructions that make up the more abstract statements and constructs from high-level programming languages. But what's significant about machine language is that, and the reason why I'm presenting it right now, is because machine instructions are what are executed natively by the hardware. So what this means is if I ask you to build a processor, what I'm really asking you to do is to design a digital circuit that can execute instructions in this form, in the form of an instruction set architecture. In other words, I'm asking you to implement an instruction set. And by doing that, you're building a processor, right? It's the same idea. So most of this, I'm going to go through this really fast because most of this should be a review from 2.12, although it's been a few years since you've had 2.12. MIPS operates on registers. Excuse me. So you've got this set of registers, which is a little confusing because a MIPS register is an addressable RAM location. Whereas previously in this same course, I presented registers as being a multi-bit flip-flop. They're different things, right? So when I say registers in this chapter, I mean architectural registers, meaning addressable units of data that can be addressed, written, and read from and written to by a program. Those are registers. You guys with me? It's a little confusing, but these registers are temporary holding spot on the chip in a very fast memory that are used for computation. So the idea is that you pull in data from memory and you put it in the registers, then you crunch it, you number crunch it, you compute with it, you do your arithmetic, and then you store the results back to DRAM. And that's the general flow of any program. Sometimes instead of storing it back to DRAM, you store it to an I/O device if your goal is to send a packet on the network or display a graphic on your monitor. But that is also handled through a load store type interface. So ultimately, if you're doing graphics, you're bringing pixels into the registers, you're processing the pixels, and then you're storing them back out, right? So the registers are a temporary holding spot for data for the processor to do computation with, right? So that's called a load store architecture, right? You load in, you process it, you store results out, okay? So MIPS has 3 instruction types. There's R type, I type, and J type. This refers to, this is a little confusing too because the instruction type refers to 2 things. It refers to the encoding. It's the way that you take the assembly language instruction and you convert it to machine code using sort of a format, right? That's the instruction format, right? But the reason why they have letters R, I, and J is because they also refer to the type of instruction that you put in each one of those formats. So R type is a format, but it also refers to any instruction that processes just on registers, that just has registers as inputs and outputs, right? Makes sense, right? Because that's what I just got done explaining. You bring in data, and then you just process the data on the registers. That's an R-type instruction, and then you send it back out. I-type is the instructions that do the bringing the data in from DRAM and sending it back out. Those are I-type. So the loads and stores are I-type. I refers to immediate because you need to put an address inside the instruction. So I-type instructions are what brings the data in, R-type instructions are what processes the data, and then use I-type instructions to send it back out. And then J-type instructions are for jumps. So that's whenever you want to call a function or a method. Use a J-type. Right? And those are the 3 types of instructions. Pretty simple. So R-type looks like this. It's remarkable in that you have 3 register fields and a shift amount for the shift instructions. The shift amount is like a little constant. And then there's a function code that tells it what to do. That's it. Pretty simple. I-type is 2 registers and 1 big immediate. That immediate can be used for an address if you're doing a load or store, or it's used as an offset for a jump, sorry, not a jump, but a branch instruction. It tells you, how many instructions to skip if you're going to branch. And then a J-type is just devoted mostly to an address to jump to. This is for calling a method. This is where you put your method address that you want to call. Method, function, subroutine, whatever you call it. Okay? And that's it. Pretty simple. So to implement these, you have to design hardware whose ultimately its inputs are connected to these fields of each instruction type. Right? So you can kind of see where this is going. The instruction originally comes out of a memory. So you have this thing called a program counter, which that's why the counter was in the last chapter, because that was alluding to the program counter, which keeps track of where the processor is in your program, what instruction it's on currently, what instruction it's executing, right? So you got that counter is what starts everything. So that's a counter that's also treated as an address that goes into a RAM. The RAM spits out the instruction. The instruction has fields, each of which is just connected to a different module inside your CPU. The 3 register fields are just simply connected directly to a RAM, which forms the register file, the address bits on the RAM. The RAM is 32 deep, 32 rows, right? So log base 2 of 32 is 5, and that's why they're 5 bits each. So you just connect these directly to the address bits of a RAM. The shift amount is connected to the input of a shifter, which we covered a shifter. We covered shifters, barrel shifters, in the last chapter, right? In the function code, remember we covered the ALU in the last chapter that had that function code that told the ALU what to do. You just plug that into that. And I'm oversimplifying this, obviously, but that's basically what's happening here. You just take these guys and you just connect each one of these to each one of the things we talked about in the last chapter. That's basically what's happening. Now, there's a lot of details we've got to work out. Yes?
For the ITAP instructions, if there's only 16 bits devoted to the address, then can that only handle 2 to the 16 words of memory?
That's right, yeah. The way they get around it, though, there's a little bit of a hack they use to get around it. So there's an immediate field. They use the RS, one of the registers, as an indirect pointer to a base register. So there's an address inside the register. The register file holds addresses too. I should have mentioned that. In addition to intermediate results for computation, it also holds addresses. So you'll have an address in the register file, and then you'll take that address out and you'll add the immediate to it, right? If you're doing a load or store. And that gives you an effective address. That's how you get to 32 bits. Oh, by the way, we talked about sign extension in the last chapter too. That's where that comes into play, by the way. You take the 32-bit address, you take the immediate, you sign extend it to 32 bits, and then you add them, and you get an effective address.
I mean, isn't the immediate unsigned? Sure.
No, it depends on the instruction, actually. It's usually signed. If it's a load or store, it's signed. The thing is that bit 15 is the sign bit here.
If it's a load or a store, is the immediate contributing to the address of the memory?
Right.
So the address would be unsigned, wouldn't it? Or
the address is unsigned, but the base register is, you may have a base register that's actually, that might have an address that's higher than your target address, in which case you would have a negative immediate, which would bring it down from there, right? In other words, the immediate allows you to refine, like you have a base address, and the immediate allows you to refine that, a base address. One of the examples of that, by the way, is for stacks. Whenever you call a function, you take all your local variables and your return address, and you put them on a stack. The stack grows down. So the base address is where your top of your stack is, and then when you put stuff on the stack, you actually have a negative immediate, and you stick them on inside the stack frame. So yeah, no, it's actually signed, but the address itself is unsigned. Okay, all right. So I'm going to get a little bit more. So I'm basically going to spend the rest of the semester just trying to refine these ideas down as much as I can to the point where you have enough information to actually build your own processor. So just to kind of go back to the beginning here. you have a program. So you start out with a high-level language program written in C or whatever language you use. That gets compiled into an assembly code program, which is assembled into machine code, which is binary, which you form. You go from here to here by just using the formats, the instruction formats, right? And then the machine code is then, when you load the program to execute it, like when you run your program, that machine code is taken off disk and it's put into memory, right? So the loader puts this into memory, and then the program counter is responsible for addressing that memory to fetch individual instructions out, to read individual instructions. The program counter is a counter because under normal conditions, programs are executed sequentially, just one instruction after the next. Now, if you run into a branch or a jump, you might interrupt that pattern and skip instructions. But under normal program flow, the program counter just increments, and that counter is used as an address, and you just pull data instructions out one by one from the memory. You guys with me? This, by the way, is the source of just about every security problem ever devised. Because the idea is that we expect that this instruction memory is only ever written to by the loading program, the loader, right, when you run your program. But if another program were to write into this memory, then it would take control of your computer. And thus, you have a malware, right? And there's been a lot of, obviously, there's a lot of infrastructure in place to prevent that from happening. But generally speaking, instructions are just data that are put into a specific spot and are read as from the RAM. They're put into the RAM somewhere. Okay. Instructions. Let's see. We've got different types of instructions. There's logical instructions, which just do bitwise logical operations. Most of you probably never done much of this. You ever done logical operations in 145, 146, 240, maybe not? Usually these are for bit manipulation, right? When you're trying to pull bits out of a value, they're not very not super common. But the idea there is, like, if I do an AND instruction, that would mean I want to take two register values out of the register file and then do a bitwise AND and then store the result back to the register file. Right? So I would be doing that if I were doing bit masking, like if I wanted to zero out parts of a register but not the whole register, for instance. There are shift instructions, which are used whenever you do the greater than operator in Java or C. Those just take advantage of the barrel shifter. We talked about shifting. Again, these are more common because these are used anytime you have to, almost any kind of bit manipulation uses shifting instructions. And then you've got branching, which is how you implement constructs like if statements and loops. So there are branches and jumps. There's a little bit of weird terminology here, by the way. A branch and a jump do the same thing. They interrupt program flow. Instead of going one instruction after the next, a branch or a jump interrupts the normal counting sequence of the program counter. It allows you to jump ahead or jump backwards, right? So why are they named differently? Well, branches are usually, the convention is a branch is conditional. So you don't do a branch unless there's some condition that's met. So you'll check to see if A equals B, then branch. Otherwise, treat this like it was a waste of time. Just keep going. Don't do anything, right? Jumps are unconditional, and those are used for method calls, like when you call a subroutine, you call a function. That's a jump. It's unconditional. So branches are used for ifs and loops, if statements and loops, and jumps are used for subroutine calls. So you got branch if equal, branch if not equal, jump, register, jump, and link. You guys remember this, right? Okay. All right, so I'll skip over that for a minute. Okay. All right, so another thing I want to mention is RAM. Computer RAM, main system RAM, core RAM, main memory. Both the memory itself, the hardware, when you buy memory at Best Buy, you buy the DIMMs, you buy the memory. Not only that, but also the conventions used by all compilers and all the compilation tools are all byte addressed, meaning that everything is treated as all memory is treated as an array of bytes, right? So an address represents which byte. But processors don't operate on bytes. Processors don't really have any concept of what a byte is. Processors all use a word, and the word is going to be either 32 or 64 bits these days, right? So you think of a 64-bit processor, that means a 64-bit word, meaning that all of the buses, the registers, the ALUs, everything inside the CPU is 64 bits. But yet, anytime you do a load or a store, anytime you interact with memory, you're dealing with bytes, right? So that's kind of strange, especially since nothing really fits in a byte anymore. But this is kind of a holdover from, you know, the 60s and 70s when these things were formalized. So as a result, there's this idea of word address, but don't let that confuse you because data is addressed by bytes. So word address 0 is byte address 0, but word address 1 on a 32-bit word would be address 4, right? So everything's going to be multiples of 4, essentially, if you do loads or stores. Okay, so how about, let's talk about load. So this answers your question from earlier. So if you do a load instruction, you give it a register, right? That's your base register, and then you give it an offset. And the offset goes in the immediate field. This is in the RS field, and then this value that you're loading into is the RT field, right? So in other words, this is an I-type instruction, 2 registers, 1 immediate. This does a load. This instruction would almost certainly crash your computer because this base register probably has an address in it that is a multiple of 4, and 5 is not a multiple of 4. And thus, by adding these two numbers together, you would get a sum, an effective address that's not a multiple of 4, and you get an alignment exception, which would cause an exception, and you go in the operating system, and it would kill your program. In Linux, you would get probably a seg fault, I would imagine. Seg fault or bus error, one of the two. In Windows, it would be a general protection fault. Well, they don't call it that anymore. I guess it just says, uh-oh, something happened. Press force quit to close your program, right? Back in the day, they would be a little bit more technical, even though they were developing operating systems for non-technical people, and they would actually have a, GPF with a bunch of hexadecimal addresses on it, right?
That would be a bus error.
Yeah, it might be a bus.
Bus error means that whatever address you're trying to access isn't something the hardware is physically capable of accessing.
Yeah.
A segmentation fault would mean that you did something even you didn't want you to.
Yeah, but it depends.
On a word-aligned architecture, this would be a bus error.
Yeah. You have to try it. Let's see. I think I agree with you, but I think the error messages have been sort of generalized. I think everything is kind of a seg fault now. But I'll have to see what happens. But anyway, yeah, this would probably crash. So this is a good example because this shows you something that you would not want to do. Usually this number would be divisible by 4. But anyway, yeah, so the address calculation is you take whatever's in the base register and you add this number, right? Now, I used to always wonder, when I first started learning this, I looked at this and said, okay, yeah, that makes sense, but who sets the base register? And when? That's usually done by the assembler. So no human will ever do that, even if you write an assembly language. You don't have to ever worry about that. Usually what happens in assembly language, you wouldn't even use that kind of addressing, actually. You wouldn't even do this in assembly. You would do this. You'd say load word, S0 would be my destination, and then I would say foo. I'd give it a symbolic name. That symbolic name would be translated into this by the assembler using the symbol table. So the assembler would have a symbol table, and the assembler would also treat that like a pseudo instruction, and it would put in a sequence of instructions to implement that one instruction, part of which would be setting up a base register with a load immediate instruction. Okay, so yeah, so this is a little bit misleading. Generally speaking, even as an assembly language programmer, you wouldn't even operate at that low level. Okay, so I went through that already. I already talked about that. Everything's multiplied by 4. Yeah, so this is a nice picture. So this shows word 0, word 1, word 2, word 3, and then the address would be 0, 4, 8, and 12. And then you can see that you've got individual bytes in there, right? But this causes another problem, by the way. What happens with this is your memory now sort of becomes kind of a two-dimensional array, sort of, where you've got one dimension is words and the other dimension is bytes, right? So if you've got memory organized, everyone's got memory organized like this, you give it a word address, and then for every word address, there's potentially a byte address if you wanted to select one of the bytes out of there. You guys with me? So how do you deal with that? If the byte address is usually the lowest order 2 bits, so it's 0 to 3 of the address. So if my byte address, let's say my word address is 3, my byte address is 2, which byte am I getting? Well, obviously I'm in this word, right? This is word 3, but which byte? If my byte address is 2, which byte? F3? That's right. If it's Little Indian addressing. If it's Big Indian addressing, it would actually be 0F. You might say, why? Well, you guys said F3. Why'd you say F3? Because you assumed that was byte 0, byte 1, byte 2. You were counting from the right. But if you count from the left, it would be 0, 1, 2, right? So is it 0, 1, 2 or 0, 1, 2? It's either going to be F3 or 0, 7. Well, most architectures are Little Indian, right? But there's a weird consequence of Little Indian. Think about what that means. That means if my address is all zeros, am I getting the first byte in the memory? No, I'm actually getting the third byte in the memory. The third byte, because it's going to be the rightmost byte, the least significant byte of that word, right? So that's called Little Indian. So if you ever see Little Indian and Big Indian, that's what that's referring to. It's the way that you extract pieces out of a word and how you interpret the offset bits to get the piece. Okay, all right, great. So that gets us past all the review stuff. Now let's start building a CPU up. So one of the issues with the first CPUs was people were worried about making a CPU that worked, right? So this is when we got like the first Intel CPU and the IBM mainframe processors, right? The VAXs. They just wanted something that worked, and ideally, their secondary goal was something that was easy to program in assembly language, right? Because they didn't have compilers back then. Everything was assembly language, and at best, punch cards, assembly language on punch cards at worst, right?
I remember when my parents used that.
Yeah. So that was the goal, right? Nobody really thought much about performance or energy efficiency back then. They just wanted something that worked and that was easy to program, right? But in this day and age, performance is the first thing you think about before you even start designing a processor instruction set architecture, right? So I mentioned the RISC-V. The RISC-V, and MIPS for that matter, even going back to MIPS, were designed from the beginning with one objective in mind: performance. They wanted the things to be as fast as possible, even if it made them harder to program, right? Because no one programs in assembly language anyway, so who cares? Let the machines do that, right? A compiler, right? So before we even get started, in the book, you'll see this in the book starts talking about processor performance before we even get into it gets into processor design. That's kind of crazy, right? So that's why we're talking about this now. You might say, why do you segue into performance? It's because the performance equation is going to drive the design of the microarchitecture, because this is our goal, is to figure out what our goals are, what our objective is in terms of what are the factors we're trying to minimize or maximize here in the performance equation, and then design our instruction set around that. So execution time is the number of instructions executed. This is the dynamic instruction count, right? This is the instructions that are executed, not the instructions that are in the program, right? What's the difference? Anyone know? Like you might have a million instructions in your program and you run it and it runs a billion instructions. And you're like, what? Why does it do that? It's because it's got the jumps and the branches, right? You got loops. You got loops that execute the same instructions over and over again, right? So this is the dynamic instruction count. And then you multiply that by the number of cycles per instruction. Now this is important, by the way, CPI. This is important because this term is what connects your program in terms of instructions and the microarchitecture, which operates in cycles, right? This is the bridge. This is cycles per instruction. This is the ratio that relates how many instructions you execute, which is a very abstract thing, kind of, right? And the actual low-level details of the digital logic design, which operates in clock cycles, right? And then you have the seconds per cycle, which is the clock rate. Well, actually, that's the clock period. The rate would be cycles per second, right? But this is the clock speed, right? Cycles, seconds per cycle. So 1 gigahertz processor would be 1 nanosecond, 1 billionth of a second per cycle. That's what that refers to. Okay? Anyway, so how do we get this execution time down? Well, we can reduce the number of instructions, and in the old days, that's how they did it. That was the main approach. So what you ended up with was instructions that did a whole lot of work, because one instruction. And that also reduced the amount of memory you needed too, right? If you had less instructions. Make sense? Although I just contradicted myself, because less instructions for memory usage would be the static instruction count, and this is the dynamic instruction count. But you get the idea, right? If we had a smaller program, even when we ran it, we'd do less instruction. We'd execute less instructions, but the instructions would be really complicated, and it would make it hard for once the compilers came out, compilers couldn't use them because they did so much. It was like you had an instruction that did like a complex number multiply, and then the compiler had to figure out where in your C code you were doing a complex multiply in order to use that instruction. And so you ended up with some instructions that didn't get used very much. So nowadays the goal is to try to, memory is cheap too, so let's not worry so much about this, and let's try to get the number of cycles per instruction as low as possible. And so these days you end up with instruction sets that are very wordy, that execute a lot of instructions, but each individual instruction is really fast, right? So this term is lower. And then seconds per cycle, it used to be that we tried to get that number up, or actually down, by increasing the clock rate. But as I mentioned at the very beginning of the semester, we can't really do that anymore, right? For a variety of reasons, but we're kind of locked in at 4 gigahertz. Can't really go any faster than that. That's 250 picoseconds. Can't really go much lower than that, realistically. All right, so so let's start building this out. So as of chapter 5, we have all the pieces we need. We have a program counter, which is a counter that is 32 bits because it's matched to the address of our memory, right? Actually, that's not shown as a counter. That's just being shown as, right now, it's just being shown as a register. This is a regular register now, just a flip-flop, right? There's PC prime, which is the next PC. and PC. So this is the next PC and the current PC, right, on the D and Q, right?
Oh, great. I didn't think we were going to be dealing with this again. I'm
Yeah.
looking forward to the slides.
Then we have an instruction memory, which is a one-port RAM. You got an address coming in and a data going out. So you give an address, it gives you the data that's in that address, right? Instructions are in here, so we're basically taking an instruction address and it spits out the instruction of that address, right? So our program gets loaded into this guy, right? Now you might say, well, is that on chip or is that off chip? Where is that memory? It's not really. It's generally going to be on. There's going to be a cache, right, where this will be on chip, and then if you need more than fits in the cache, then it would be backed up by a larger off-chip memory, right? But this is this is our instruction memory, and then we have a register file, which is a RAM, an SRAM. But this one is just like the instruction memory. It's just a RAM, except it's smaller. Notice it only has a 5-bit address. So this guy is 4 billion depth, and this is 32 depth based on the address, right? But it has more ports on it. It has 2 read ports and 1 write port. Now you might say, why? Well, that's because the instruction set is designed around that concept. All the R-type instructions presume that you can read 2 registers and write 1 in 1 instruction, and we're going to try to do, in order to try to minimize the cycles per instruction, we want to try to do an instruction, everything required to do 1 instruction in 1 cycle, and thus we need a 3-port memory here for the register file, right? Now you could say, what if I just want a 2-port register file or 1 port? It's fine, but then it's going to take you 3 if it's a 1-ported register file, it's going to take 3 cycles at a minimum to do an R-type instruction, right? Because you've got to read your 2 inputs and write your output. Yes?
The distinction between instruction memory and data memory, is that different from how x86 does it?
Yeah, there is a there's really only one memory. There's only one physical RAM in your computer, right? So instructions and data share the same RAM, and they share the same address space. They even share the same virtual address space. If you have an MMU, you have virtual memory addresses. So there's one address space. So you can't have one address that has instructions if it's accessed on this guy, and data if it's accessed on this guy. The instruction, the space of addresses is common, right? The fact that there's 2 physical memories are there because we're going to do a single cycle CPU, right? And so in order to implement in order to be able to fetch the instruction and possibly also do a load or store if it's a load or store, requires that you have essentially 2 ports into your memory, right? And these guys actually represent the 2 ports, really, right? So they're not different. It's a little bit misleading. It's a good question because it's a little misleading because you might say, is this a different memory space than that? Like if I go, like let's say I write address 0 on this guy. Let's say I read address 0 on this guy. Is that the same data I'm referring to? Yes, because it's one unified address space. Usually, it doesn't have to be. Actually, we've done some FPGA designs that don't follow those rules, but in general, that's kind of the presumption on a typical computer. But for some reason, these textbooks always show these as 2 separate memories. These kind of just represent 2 ports. In reality, on a CPU, you're going to have an instruction and a data cache, right? So you do have 2 physical memories on a real processor, but those are just caches of a much larger memory that's a unified memory, right? Does that answer your question? Yeah, it's a little confusing. There's also this notion of a von Neumann architecture, and then there's a Harvard architecture, right? There's 2 different architecture styles. Von Neumann architectures have a unified memory, and a Harvard architecture has a split instruction and data memory, right? So sometimes you'll hear people refer to this as a Harvard memory, a Harvard architecture, right? But the distinction is artificial because with memory hierarchies, typically, even if you have 2 instruction data memory split at some point, eventually they're kind of down the memory hierarchy. They're in a unified memory address space. Does that make sense? Okay. All right. So the way you got these connected is the program counter is pretty much wired just directly to the instruction memory. That's pretty easy. Just draw a wire. Well, again, it's not one wire, it's actually 32 parallel wires, but when you draw block diagrams like this, multi-bit signals are drawn as one wire. Something you got to get used to. Whatever comes out of there is also one wire that represents the instruction. It comes out, and then what do we do with it? Well, we start splitting it up. And we split it up according to the fields in the R-type, I-type, and J-type instruction format. So I'm going to take bits 25 down to 21, and I'm going to plug those into the first port on the register file, right? And then I'm going to take bits 15 down to 0, that's the immediate field, and I'm going to put that into a sign extender. You guys remember we talked about sign extending in chapter 5, right? That's when you take the sign bit and you replicate it 16 times to convert this 16-bit value to a 32-bit value, right? Okay, so you should be able to tell already that we're talking about an I-type instruction right here. This is the example this example is an I-type instruction. Okay, and then we got an ALU, which we covered also in last chapter. This is the same ALU. I wonder if I can pull that up real quick here just to. I went too far. Oh, no, maybe not. Was it before? It was before. Oh, yeah. Set less than. Yeah, this guy. Yeah. Was it this guy? Yeah, this ALU, which was. Yes, this guy. So you guys remember this ALU design? So this is the ALU that we're using here. It's basically this thing that can do. It has this operation code that comes in, F function code, and it's only 3 bits. So there's 8 possible things this thing can do. There's 8 different encodings, although this one's not used, so there's 7. So this thing can perform 7 functions. It can do bitwise and, bitwise or, add, and then it can do, like it could do an and where the second input is inverted or complemented. It can do an or where the second input is complemented, a subtract, or a set less than. Yeah, so these are the things the ALU can do. So there's an F, there's a function code F, there's a 3-bit function code, and then there's an A and B that are 32 bits, and then there's those inputs, and there's a Y output. Okay? So that is the ALU that's being shown here. Notice also they added this little thing, 0 output. I alluded to this when I first talked about the ALU, that sometimes you care, like if you want to compare 2 numbers to see if they're equal, you might just subtract them and check to see if the result is 0. So this is a flag. You see how this is a thin line as opposed to the thick lines that are shown here. This means it's 1 bit. It's a flag that just 1 if the result is 0, and 0 otherwise. And there's the 3-bit ALU control. And then the ALU result feeds into, now you would think this would feed back into the register file, and it does, except this example is a load. This is a load store example. So in this case, we've got the ALU result going into the address on the data memory. So why? Because this is the ALU is calculating the effective address. You're taking the source and you're adding the offset, and you're using that as your effective address for a load or store. Okay, so if you do a load, you get the address calculated, you stick that into the address on the data memory, then you read the data at the word at that address. It's word addressed. You hope that whatever the ALU spit out was evenly divisible by 4, or you'll get a bus error in Linux. The read data, assuming you're running Linux on this, you got the read data from the memory, comes back and goes into the write port on the register file, and the location that we're writing to is bits 20 down to 16, which is the RT field. Now I don't know if you guys remember this from 2.12, but if you do a load instruction, right, it's an I type, so there's really just 4 pieces in the instruction, right? There's an opcode that tells it what instruction it is, 6 bits. Then there's 2 5-bit registers. One is this guy, the base register, and the other one is the destination register. So that's 6 plus 5 plus 5, that gives you 16 bits. And then the other 16 bits are used for this immediate, right? So I've used up every piece of the instruction. Like the American Indians, they use every piece of the buffalo. I use all the bits up for their designated purpose. I don't waste anything. And, oh, and then you have to tell the register file there's a write enable. If you remember from that Verilog I showed you. You don't want to, oh, you only want to write when you really want to write, right? You only want to write when you intend to write. You only want to write if you're executing instruction that writes to the register file, which is just about every instruction except for branches and jumps. Right? Everything, oh, and stores. Stores store to the memory, they don't store to the register file. Branches and jumps just manipulate the program counter. Everything else has to write its result back to the register file. Right? Including load. So what are we doing with a load? We fetch the instruction. In this design, we're assuming it's a load. Normally, you'd have some control logic that checks that, but this thing only does loads. This hardware design right now can only execute load instructions. So the load comes out of here. I grab the register for the base register. I grab the contents of that, put in the ALU. I get the immediate, sign extend it, put that in the ALU. I add them together, feed the result to the instruction. To the address on the data memory. That'll give me a corresponding contents of that memory, which is then shoved back into the register file and written to, and that's my load. Make sense? Okay. When I first took computer architecture, I used a textbook called, there was this guy Mano that wrote in fact, I think they still are coming out with new editions of that. They used to teach this in the Mano textbook. This was a competitor, Hennessy and Patterson. And obviously this textbook that we're using in this class uses the Hennessy, builds on Hennessy and Patterson. That was the 212 textbook. In my class, they used to not rely on block diagrams. They used to use register transfer language to show what's going on here, right? This is an alternative form. This is where you say, so you can define what's going on here using like a programming language called register transfer language, which is kind of like a pseudocode sort of for hardware, right? Except it's at the abstraction of, it's at the data path extraction. So these are all data paths, right? So the idea is that what's really happening is I could think of it this way. I could think of an instruction register is getting the instruction memory, whatever I want to, this, right, of PC, right? And then ALU A, which is that first input on the ALU, gets the reg file of IR bits 25 down to 21. Right? So this is the way register, the idea is that we want to be able, now these are all concurrent, by the way, there's no ordering here, right? But you can see that every cycle I'm going to do this operation which updates this signal, and then this guy is going to get triggered because the IR updated, right? So this is the way that you would describe this in register transfer language, right? See, I was confused when they taught it like that, right? I was kind of like, oh, it kind of looks like a programming language, but it's really not. Whereas this is more representative of the actual hardware. But to understand what's going on here, you have to also understand the behavior of every one of these blocks, and you have to be able to trace the data flow through this thing. You guys with me? So if you're confused by looking at this, which you easily could be, because it's just a bunch of blocks with wires, right? You have to think of it, you really have to think of it as these are memory, and you sort of have to start here, and you have to sort of read from the left to the right. And you have to understand how all these memories work, right? And this is all happening in one cycle. This is a single cycle CPU. So the only thing that changes on the clock edge is the program counter, and everything follows suit from there. Well, actually, this register file is also synchronous too, because the writes are synchronous. So everything begins with that and ends there on the clock edge. You guys with me?
Yeah.
So what do you think makes more sense? Just kind of writing it out as a sequence of register transfers or showing it as a block diagram? They're equivalent, but Hennessy and Patterson always presented this information this way. Mono always did it like that. This is a little bit more, this is closer to what you would be dealing with if you were physically designing a CPU. So that's why this is more of a design-oriented approach. That's more of a kind of like an algorithmic approach, right? Okay, so good. So this is great. Looks we're out of time, and we'll see you on Wednesday for our final class meeting till the final.